Good afternoon. My name is Tyler Landua, and I'm an undergraduate student at the School of Oklahoma State University, and I'm a mechanical and aerospace engineering major. And today I'm going to talk about large eddy simulation around buildings and crosswinds with a focus on unmanned aerial systems. And so for the first slide, we'll talk about some buildings and crosswinds. And so unobstructed airflow is ideal for light aircraft, but is very rare in nature. And so buildings and terrains and different wind flows all present complications in flow characteristics. And so just to define an unmanned aerial system is a pilotless aircraft which is flown without a pilot in command on board, and these can be flown either remotely or can be programmed for full automation. And here's some problems delaying integration of UAS. And a key issue preventing the full integration is really the unpredictable behavior of the aircraft. And a couple of key components of this unpredictability are the ability of the pilot and the timeliness of response and control. And both of these issues, both the ability of the pilot and the timeliness of response and control, can be made more difficult by adverse flow conditions. And these flows can be impacted by wind and geometry, and since UAS are typically very small, that means that the flow around them impacts them in a very heavy way. And so why did we use large eddy simulation? And it's more accurate than the Reynolds average, Navier-Stokes, or RANS, since the large eddies account for the most of the turbulent energy and momentum transfer, and LES captures these eddies in detail and fully resolves them, while RANS simply will model them. Direct numerical simulation could also be used, but its computation time is much heavier, and it can only be done on simple geometries and low velocities. I used Palm to carry out my large eddy simulation, and it uses a 3D Cartesian structured grids that are analyzed over a domain with a flat surface at the bottom, and the two buildings will be situated within the flow. And so the two cases that I analyzed are going to be the tall building and the short and rectangular building. So we'll start off with the tall building. And so the tall building simulation setup, the domain size was a 200 by 100 meter by 82 meter rectangle with a grid size of 2 meters equidistant. And the building size in this tall building is going to be 41 meters high by a 21 meter square footprint. This building size is approximately 12 stories tall, so you could think sort of like an office building. And it has a neutral boundary layer and initial flow velocity of u equals 4 meters per second. And the right and left boundaries are non-cyclic, with the top boundary with a free slip condition. And the simulation time was 1.5 hours, with data collected every 3 minutes. So the results of this are going to be contours of u, v, and w velocities colored based on magnitude, and this coloring is used for visibility and might be exaggerated during the entire time domain, and each frame is going to represent a 3-minute interval. So we'll start off with the u velocity component of the tall building. This is the velocity in the x direction. And you can see on this vertical view here, the scale dips into negative velocities, and those are those lighter colors behind the building. And this is an indication of circulation behind the building. And you can see on the right image is the horizontal view, the same idea with the circulation in the lower half of the building behind it. You can see that this flow goes all the way to negative 2.2 at the lowest value on the scale there. And the flow peak velocity at the top as the flow goes over the building is about 6 meters per second. And then the w velocity, this is the velocity in the z-axis. You can see that for the most of the domain, it's about 0, which is good because we did not initialize a velocity for this component. But you can see in the vertical view, you can see these really good circulation pockets behind the building with flows ranging from 2 to negative 2 meters per second. And those are those red areas in the flow behind the building, indicating that there's vertical flow in these regions, which is another indication of circulation. And you can see on the right plot of the horizontal view the same idea. As the flow goes over the front corner of the building, you can see there that little red pocket. That's just indicating that there's flow in the vertical direction there as it's going over the building. And this is the v velocity, which is going to be the velocity component in the y direction. You can see on the left plot this vertical view. This is to be expected. You have an area of high velocity and negative velocity on the top and the bottom of the building, respectively. This just means that the velocity is going around the building, and this would be expected. And now to analyze the short and wide building. The domain size and grid size are going to be the same, and this building is going to be 25 meters tall instead, and this is going to be 10 meters long and 42 meters wide. This is approximately 7.5 stories tall and might represent your average apartment building. And we have the same initial conditions, and the results of this are going to be the same, colored based on magnitude, and the results are shown during the entire time domain, with each frame representing a 3-minute interval. You can see the same idea of these negative flow regions behind the building, and these higher velocity flows as the airflow goes around and is disturbed by the building. We'll come into this W plot for velocity for the short and wide building. This is the velocity in the z direction. You can see here it has these same positive and negative values as the velocity is going up and down. And the z direction, this is another indication of circulation again behind the building. And the v velocity, this is going to be the velocity in the y direction. You have the same idea of a high velocity region towards the top of your screen and a low velocity region. This just means that the flow is going in the positive and negative y direction. And then you can see this good circulation behind the building happening in the y direction. And you can see the same idea in the horizontal view, where you can see where these regions of high velocity flow are in the y direction, and then these lower velocity and negative velocity regions. So for the verification of the tall building, we can see here that E star represents the turbulent kinetic energy, and it has converged after a short period of time, signifying that the turbulent flow is fully developed. And for the tall building, we're continuing on to Umax. You can see that it ranges from 6 to 6.4. Vmax ranging from 4.2 to negative 4.1 as that flow goes in those positive and negative y directions around the building. And Wmax ranges from 5.56 to 5.61. And the verification for the short building, you can see again, save for a spike in about the middle of the time domain there, the turbulent kinetic energy reaches relative convergence. And the Umax is much more stable for this case, but has those two little spikes into negative 8.2. And the Vmax for the short building, you can see ranges from negative 5.8 to 5.1. This is also to be expected. And for Wmax, you have it ranging from 6.17 up to 6.35. So how does this affect UAS? We're going to consider this is the taller building, and this region highlighted on the chart to the right shows the changes in U velocity over the time period. And you can imagine that a UAS attempting to fly through this region in space would face heavy flow variation with a possible maximum of 137% decrease in flow velocity from that end nut velocity of 4 as the data goes all the way to about negative 2. And the same velocity disturbances can be seen in the W and V velocities for this tall building. And we'll continue on to this short building case, and the effect of the wider building has an even more pronounced effect on the velocity behind it. As you can see, the values for this one range all the way from negative 3 back up to 4 meters per second as the flow crashes back together from being disturbed by the building. And these variations in flow create an extremely complex environment for a UAS to navigate as it travels behind a building. And we could expect an even more disturbed flow area when we're taking variable inflow velocity into account. As the wind is rarely ever one constant speed, you would have these gusts that would create an even more complex and pronounced area of disturbance behind the building. And presented in this animation here to the right is a W throughout the domain represented as a volume, and this bubble in the front towards the sort of lower left of the animation represents where the building is, and you can see behind it there all of the variations in flow that range from 2 meters per second to 0.2 meters per second. And so some conclusions. We can conclude that the flow around buildings is complex and variable, and that these conditions greatly increase the difficulty of operating a UAS in an urban environment. And the solution in aiding the control and stability of UAS in complex flows has to be developed before UAS are introduced into urban environments to reduce the chance of accident or damage. And this research shows the importance of designing buildings which produce a minimum aerodynamic signature as well. And this large eddy simulation can be used to generate aerodynamic footprints of buildings or urban centers, which can aid in more areas than just drone integration, such as urban development and zoning of other buildings. And we'd like to acknowledge the National Science Foundation and some of the computing power that was provided by the PEAT supercomputer at the High Performance Computing Center at Oklahoma State University. Thank you very much for your time, and I hope you have a good day.